Hi everyone, the topic for this video will be significant figures. We have to start our studies somewhere, and I've chosen significant figures as the first topic that we study. You'll probably see them in other classes. It's not my favorite subject, but let's get it out of the way. So the number of significant figures in a measurement reflects its degree of certainty. When multiplying or dividing two numbers, the number of significant figures in the result is the same as the number of significant figures in the number, with fewer significant figures. So you only keep the number of significant figures is the same as the number of significant figures in the less precise measurement. When adding two numbers, keep significant figures only up to the first uncertain digit, and integers and mathematical constants effectively have infinite significant figures. So you get to use as many significant figures as you want for those. All right, so what are significant figures? The number of significant figures in a measurement reflects how certain that measurement is. So if a number has more significant figures, it's known to a greater precision or greater certainty. For example, suppose Ruth, Veronica, and Michelle each measure a small object. They're all measuring the same object. Ruth uses a ruler, Veronica uses a set of vernier calipers, and Michelle uses a micrometer. You don't need to know what vernier calipers or a micrometer are. Just know that they're used for measuring lengths. They respectively find that Ruth measures L is 2.47 centimeters. She finds that with a ruler. Veronica finds that it's 2.458 centimeters. And Michelle finds that's 2.4592 centimeters. Okay. These measurements have 3, 4, and 5 significant figures respectively. So let me try and convince you of that. Ruth's measurement has 1, 2, 3 significant figures. Veronica's has 1, 2, 3, 4 significant figures. And Michelle's measurement has 1, 2, 3, 4, 5 significant figures. So that's how I'm counting significant figures. Basically, any digit that's not a leading zero counts as a significant figure, although there's some interesting cases around that, and I'll talk about them briefly at some point. Okay, so we say that Michelle's measurement is the most precise, while Ruth's measurement is the least precise. And that's a general fact about micrometers and vernier calipers, is that a micrometer is the most precise instrument that you can use, and a ruler is a less precise instrument. So let's talk about a real measurement. Let's look at a real world example. This is from another video that I made concerning one-dimensional motion. It was a lab about one-dimensional motion. And so this is real data that you're looking at. It's a piece of heat-sensitive tape, and there are some little dots on here. There's a dot here, 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 and here. I don't know how well those are showing up, but oops. But I'm going to focus my attention on this dot and this dot. And so my question is, what measurement are we looking at? Well, the meter stick is lined up with the left dot. And so all we need to do is read where the right dot is. And you could just round up and say that it's 5.5 centimeters, but I think we can do a little bit better than that. If I look very closely here, I see it's between 4 and 5 centimeters. And so I might come up with an estimate of 5.46 centimeters. And that's my measurement. There are 3 significant figures in that measurement. So 3 significant figures in this measurement. That's basically the best measurement that we can come up with for this. And so if anyone tells you that they used a ruler to find that it's 5.4632 centimeters, you pretty much know that they're lying to you. This is, if you look as closely as you can, we can only maybe get one more digit out of there, up to the hundreds place in the centimeters, measured in centimeters. So let's talk about the uncertainty in the last digit. For the purposes of this video, the last digit, or the least significant figure, has an implied uncertainty of plus or minus 1. A digit in a derived quantity will be said to be significant if it is plus or minus 3 or less. And the exact rules are more complicated. There really is no hard and fast rules about whether a digit is significant or not. But we need to be able to pin down something for the sake of this video. So let's look at this video. Look at this previous example. We found that this was 5.46 centimeters. It's according to that rule that I just stated. Because this is a measured quantity, it's plus or minus 0.01 centimeters. And the fact that it's 0.01, reflects the fact that we've reported out to 3 significant figures out to the hundredths place in centimeters. Plus or minus, so it could be 5.45 centimeters, or maybe it's as large as 5.47 centimeters. But we would be surprised, maybe not out of the question, but we would be a little bit surprised if it were 5.44 centimeters or 5.48 centimeters, and we certainly wouldn't want it to be as far off as 5.4, I'll say 3 centimeters or 2 centimeters. 5.4. Let's go for the gusto. 5.41 centimeters to 5.50 centimeters, something like that. We're looking for something that's in a tight range here. Okay. So I think if you look up at this measurement, you could believe that based on where this dot shows up, that it's somewhere between 5.45 and 5.47 centimeters. Okay. So let's do some multiplication and division. I'm going to lead with some examples, and basically what we'll look at are how precisely we can pin down their results, and then I'll give you the rule afterwards. So you don't have to make a table like this every time you do a calculation in this class. So I just pulled some numbers off the top of my head. Let's consider multiplying 12.7 and 1.43. Each of those numbers has 3 significant figures. And I said that we assume that there's an uncertainty of plus or minus 1 in the last digit. And so the smallest that this measurement could be is 12.6. And the smallest that this measurement could be is 1.42. And so the smallest value that this could reasonably take on is about 17.892. Okay, so I'm going to report that out to 5 digits. So plug that in on your calculator. Be sure to verify that I've done this math correctly. Likewise, because there's that uncertainty in the last digit of 1, it could be as large as 12.8 or as large as 1.44. So each of those basically takes the last digit and adds 1 to it. If I take those and multiply them together, I get 18.432. Again, reporting it out to 5 digits, which is excessive. All right, look what we have here. Our low estimate is 17.9-ish, and our high estimate is 18.4-ish. It looks like we only really know it out to 3 digits. If you include these last 2 digits, that's going to be kind of excessive. So our best estimate is going to be 12.7 times 1.43. So you'll plug that into your calculator, and your calculator will happily spit out 18.161. But like I said, those last 2 digits are not significant. Those are not digits that we'll include, and so the answer that we really report is 18.2. Okay, so we only keep 3 significant figures. And again, the reason why is because 18.2 is about halfway between 18.4 and 17.9, but these 2 values disagree on that 3rd digit, and so that's why we keep it only up to 3 digits here. Okay, here's another example. 3.1 times 16.90. Well, the low estimate is 3.0 times 16.89, and that is 50.67, according to my calculations. The high estimate, if we round those last digits up, is 3.2 times 16.91. That's 54.112. Okay. And take a look at this. They both agree that the first digit is 5, but the second digit could be as low as 0, or maybe 1 if we round up, or it could be as high as 4, and so we'll basically split the difference. Let's multiply these two numbers together directly. Your calculator will tell you that that's 52.39. But not all of those digits are significant. Those last two digits are not significant because the lower bound and the upper bound disagree with each other there. And so we would report this number as 52. There's your answer, it's 52. All right, one more. 7,623 times 4.29. Well, that could be as low as 7,622 times 4.28. And I get 32,622.2. If we round those last digits up, we get 32,783.2. And if we multiply these two numbers together directly, as we would like to do, we get 32,702.7. All right, how many significant figures do we actually have? They both agree that the first digit is 3, they both agree that the second digit is 2, and then there's some disagreement in that third digit there. It's a 6 over here, and in fact it's kind of a low 6 here, and it's a high 7 here, 78 versus 62. So I would say that this has just 3 significant figures, and we'll cross out these last 3, and we would report this value as 32,700. Keep in mind that when you write that down, it's ambiguous as to whether these trailing zeros are significant or not. So we'll talk about that a little bit later. I'm not going to cover it right now. Okay, so let's put all of this together. How many significant figures did we start with here? We had 3 significant figures multiplying 3 significant figures, and we got 3 significant figures. So that's a little bit of a hint as to what the rule is. 2 significant figures multiplying 4 significant figures, 1, 2, 3, 4. This 0 is significant the way that I've written it. That gave us 2 significant figures. So we had 2 significant figures multiplying 4 significant figures, and we got 2 significant figures out. How about 4 significant figures, 1, 2, 3, 4, multiplying 3 significant figures, 1, 2, 3. That gave us 3 significant figures. And so in the products, or in the numbers that we're multiplying together, whichever number had the fewest number of significant figures was the number of significant figures that we kept in the version, in the product itself. So 18.2 has 3 significant figures, and each of these numbers has 3 significant figures. 52 has 2 significant figures. 3.1 has 2 significant figures, and 32,700 has 3 significant figures. 4.29 has 3 significant figures. So that's the rule. The number of significant figures in a product or quotient is the same as the number of significant figures in the quantity with fewer significant figures. So you never need to make this table again. You just need to remember that you'll keep the number of significant figures you keep is the same as the number of significant figures in the less precise quantity. So check that this works for division as well. I'm just stating that it does, but you don't have to take my word for it. Drop a table if you want and go through the same process with some numbers that you pick off the top of your head, making sure to specify how many significant figures each one of them has. All right, let's talk about addition and subtraction. So I've picked some more random numbers. 13.7 plus 48.6. The low estimate would be 13.6 plus 48.5, and that would give us 52.1. 13.8 plus 48.7, that gives us 52.5. Well, for the best estimate, we'll take those original 2 numbers and add them together, and that gives us 52.3. Oops. That gives us 52.3. And it's halfway between these other two numbers, 52.1 and 52.5. I see that that 52.1 is 0.2 lower than 52.3, and 52.5 is 0.2 higher than 52.3, and so this third digit is significant. It's uncertain. It could be a little bit higher, a little bit lower, but it is a significant figure. All right, 144 plus 7.18. Our low estimate is 143 plus 7.17. That gives us 150.17. Our high estimate is 145 plus 7.19. That gives us 152.19. And so let's take these two original numbers and add them together to give us our best estimate. That gives us 151.18, but not all of these digits are significant. Let's take a look. They both agree that the first digit is 1. They both agree that the second digit is 5, but then this third digit could be a 0 or it could be as high as a 2, and so this third digit is uncertain, but it is significant, and so the number that we write for our result is 151. All right. One more example. 1.92 plus 0.3. Note that this has three significant figures. This has just one significant figure. Let's see what the result is. That could be 1.91 plus 0.2, so that's 2.11. Or it could be as large as 1.93 plus 0.4, which is 2.33. And for our best estimate, we'll take the original two numbers and add them together. And we get 2.22. Okay, but not all of these digits are significant. Take a look. Both of our estimates agree that the first digit is 2, but the second digit could be as low as 1, could be as high as 3, so this last digit is not significant, and we would just write 2.2. All right, so what's the rule here? Well, it's different from the way that it was with multiplication and division. Instead, what you're going to be looking for is how many decimal places out you know these quantities. So each of these quantities is known out to the tenths decimal in the decimal place. So out to the tenths place. Each of these quantities is known only out to the units, to the units digit. So this quantity is known to two more digits, but those digits don't show up here, and so they basically don't contribute to the significant figures. How about here? This number doesn't have a units digit, but that doesn't matter because it does have a tenths digit, and this quantity has a hundredths digit, but this one doesn't, and so they both are only known out as far as the tenths place. Okay, and so that's as far as we keep our significant figures here. So what's the general rule? When adding or subtracting two numbers, write the result out to the least significant digit that they have in common. So one more time, each of these quantities is known. They have in common the tenths place, and so that's as far as we write out our result. These are known out to the units, and so that's as far as we write out our result here. And each of these is known, again, out to the tenths, and so that's how far we write out our result here. Okay, one more quick note. Mathematical constants, including integers, have infinite significant figures, effectively. So, for example, we have 4 times 57.86. Well, your calculator will spit out 231.44. But not all of those digits are significant. 4, though, it's in this context, we're not treating it as if it could be 3 or it could be 5. we're saying that this is a mathematical constant. It's the integer 4. And in that case, what you'll treat it as is 4.000000. So when you multiply that by this, we keep this out to, this has 4 significant figures, and so we'll keep only the first 4 significant figures here, and write our answer as 231.4. So that's how you'll actually write down the number. And pi plus 0.273 is equal to 3.414, because we know both of these numbers out to the thousandths place. Okay, so that's how you deal with mathematical constants, and that's your intro to significant figures.